I'm going to speak about asymptotics of intersection numbers that appear in models of two-dimensional quantum gravity. Let me start with Witten's two-dimensional topological gravity. This theory essentially lives on the modular space of smooth complex algebraic curves or Riemann surfaces of genus G with n labeled mark points. The mark points are numbered by numbers from 1 to n. Well, this is a non-compact complex orbifold, and there is a nice compactification of it that is called Dillon-Mumford compactification, and it's obtained by adding stable curves. That means curves that may have a finite number of double points. Local operators are Chern classes that are usually denoted by psi I. There are n tautological line bundles to the modular space, and the fiber of the ith tautological bundle at the point represented by a curve C with mark points x1 to xn is just the cotangent line to C at the point xi. This defines a line bundle that is not denoted by Li. And the main objects of the theory are the n-point correlators. These are intersection numbers of psi classes, and it's the standard notation for it is tau d1 up to tau dn in angle brackets. This is just the integral over the modular space of the product of psi1 to d1 up to psi-n to dn. This integral is non-zero if and only if the sum of powers di is the dimension of the modular space, that is 3g minus 3 plus n. And if this condition is not met, then these numbers are supposed to be zero. When they are non-zero, they are always positive. The total free energy of two-dimensional topological gravity is the formal power series of n-point correlators. And it looks like this. So that's the sum over n from 1 to infinity, and the sum over non-negative numbers di's that define the corresponding intersection number. The generating series satisfies the string equation and Korteweg-de Vries hierarchy, or equivalently, the system of Virasoro constraints. And this series is uniquely determined by either of these two sets of equations. That's the formulation of the famous Witten conjecture that was proven by Kontsevich first, and then several other proofs appeared, among them proved by Akunkov, Konferipante, Kazaryan, Landon, Mirzakhani, Norbury, and there are others as well. What is interesting that almost all of these proofs use some kind of combinatorics. And the only one that doesn't use it is Mirzakhani's proof. It was obtained in pure geometric terms, namely in terms of hyperbolic geometry of surfaces. So now let me show you how this system of equations look like. The first set, defining set for the total free energy F, consists of the string equation and Korteweg de Vries hierarchy. The string equation is written on the first, on top, and the Korteweg de Vries hierarchy looks like this. The derivative, we take the second derivative with respect to T naught. T naught is the space variable of the generating series F, and call it U. And then we define the right-hand sides of the hierarchy. They are called Gelfand-Dickey differential polynomials, and they are defined recursively by this formula. A non-trivial, highly non-trivial moment in this system is that the right-hand side is a complete derivative with respect to T naught. So the equations look like this. The derivative with respect to the m time, T1, T2, and so on, they play the role of times. That's R prime, the Gelfand-Dickey polynomial with number m plus 1. So as I said, total free energy satisfies this system of equation, and this system of equations determine this total free energy uniquely. Equivalently, one can consider the set of Virasoro constraints for the partition function that is the exponential of f. So the exponential of f is a highest weight vector in the Virasoro representation. Not entire Virasoro algebra, but sort of half of it, starting with m equal to -1, 0, 1, and so on. And that's how the operators of Virasoro algebra representations look like. And it's not hard to check that these operators Lm are they the Virasoro commutation relation, right at the bottom of this page. So as in the case of Korteweg-de Vries equation, Virasoro constraints determine the partition function uniquely. Let me make one remark. The first equation with m equal to -1 is just the string equation that appeared before. And the operator L naught also has a special name. It's called the Dilaton equation. And it's not hard to see that actually the generating function for the endpoint correlators is completely defined by two equations with m equal to -1 and 2. Using Virasoro commutation relations, one can express all other operators in terms of commutators of these two. So let's now move to the asymptotics of endpoint correlators. The endpoint correlators can be computed recursively using either the KdV equations or Virasoro constraints. But in both cases, this process is very slow and doesn't give any closed form expressions for the correlator, except for small g and n. There are computer implementations of these algorithms, and if you compute in a straightforward way using KdV equations or Virasoro constraints, we can compute up to genus approximately 10. And then it becomes just impossible to compute because of the complexity. So let me give now some simple examples. What happens for small g and then? The simplest case is when g is 0. It means that we live on the Riemann sphere, and there are n marked points on the Riemann sphere. The sum of indices di sums up to n-3, where n-3 is the dimension of the modular space F0n. And for this correlator, there is a simple formula, which is usually attributed to Kontsevich. And this formula says that this intersection number is just a multinomial coefficient that is written here. Another simple case is when n is equal to 1. Then we consider curves of genus G with 1 marked point, and there is just 1 point correlator, so 3G minus 2. And this correlator is explicitly equal to 1 over 24 to the G times G factorial. This was first observed by Witten, and this is a simple consequence of the string equation alone. Everything becomes much more complicated if G becomes larger than 0 and then becomes larger than 1. Let me show you the formulas for 2-point correlators. These are closed form expressions, which, however, look quite complicated. So this intersection number can be computed explicitly using the string equation, and it's the same as in the Witten's example, namely 1 over 24 to the G times G factorial. And there is a closed form expression, which is rather large because k differs from 1 to 3G minus 1 over 2, approximately. And this correlator looks like follows. So here we have some factor consisting of double factorials. And here we have a pretty large sum where the numbers b, g, I are explicitly given by this formula. So you see, that's a very complicated expression involving lots of factorials and double factorials, and it also depends on the residue of k modular 3. I got this formula a couple of years ago, and it seems that it wasn't known before that. It's not actually possible to generalize it to n, say, equal to 3, because the expressions become just wild. They already for n equal 2, it's quite complicated, but for n equal 3, it's simply meaningless to give a closed form expression. However, the life becomes nicer if we look at the asymptotics of these numbers of n-point correlators when the genus of curve becomes large enough. In particular, from this closed form expression for For 2-point correlators, one can derive the following simple asymptotic formula. We take the 2-point correlator, and multiply it by 2 double factorials to normalize it, and then this normalized 2-point correlator has a nice limit that is independent of k. And actually, the remaining term, it doesn't depend on k either. So this convergence is uniform in k. So that means that this normalized endpoint correlators for large G are about the same. So that's an interesting observation that can be generalized further. And for n equal 3 or larger, there is a formula that is not much more complicated than that of in case n equal 2. So again, we take an endpoint correlator, we multiply it by double factorials to normalize it, and take the limit in G when G goes to infinity. And then it has a nice asymptotics. This one. And the remaining term is almost as good as 1 over G. It's 1 over G to the 1 minus epsilon, where epsilon is any real number. It can be arbitrarily small, positive real number.
Excuse me?
Yes?
There's a question from the audience. Anton, please.
Yeah, sorry. So is there any intuition why G large, why G going to infinity would simplify things as you are describing now? Is there some geometric idea behind, or why such a phenomenon occurs?
Well, I don't have any explanation of that fact. It just happens.
Okay, fair enough.
We'll go with that.
So, okay, so and this convergence is uniform in indices d1 to dn as G tends to infinity. This was conjectured by Delacroix, Vincent Delacroix, Elise Goujar, Anton Zorich, and myself, and it was very recently proven by Amol Agarwal. His proof is very interesting because it brings in some new ideas to this field. Namely, he interprets the coefficients appearing in the Virasoro constraints for these intersection numbers, and he interprets them as jump probabilities of a certain asymmetric random walk. And that allows him to get a pretty good estimate. But, as I said, I don't have any explanation, simple explanation, why this normalization by multiplying with double factorials simplifies things so much. So let me now switch to Weil-Petersen volumes. These are also intersection numbers, but of a different nature, and they also appear in models of two-dimensional quantum field theory. The model space MGN has a natural Hermitian metric that is called Weil-Petersen metric. Let me define this metric now. First, we observe that the tangent space to the model space MGN at a point represented by a curve C with n-marked points x1 to xn is naturally isomorphic to the space of harmonic Beltrami differentials. That means harmonic 0-1 forms on the punctured surface, on the punctured curve, with coefficients in the holomorphic tangent bundle to the curve that are square integrable with respect to the hyperbolic metric. That follows from general theory of deformation of complex structures and a whole scalar product that is just the integral over the curve of mu wedge star mu, where mu and mu are harmonic Beltrami differentials. This scalar product gives rise to a Hermitian metric on the modular space that is called the Weil-Petersen metric, and is usually denoted by angle brackets with subscript WP for Weil-Petersen. A few facts about Weil-Petersen metric. The first observation is that the Weil-Petersen metric is scalar. That was proven by André Weil, who introduced this metric. And instead of the Hodge scalar product, he used the Petersen scalar product for automorphic forms. It is actually the same thing, but said in a different language. That's why this metric was called Weil-Petersen metric. This metric is singular at the Deligne-Marford boundary, but the Weil-Petersen volume, symplectic volume of the modular space, MGN, is finite. That was observed by Howard Mansell, who found the asymptotics of the Weil-Petersen scalar product, Weil-Petersen metric, to the boundary of the modular space, and this singularity is rather mild, so the volume is finite. Then Scott Wolpert refined this result and proved that the Weil-Petersen scalar form extends as a closed to current to the Deligne-Marford compactification MGN bar, and represents a rational cohomology class, two-dimensional cohomology class of the Deligne-Marford compactification. But that's not all. This is just a well-known cohomology class that is called the first Marford class, or the first Marford-Morita-Miller class. And this class is a standard notation kappa 1, and by definition it's just a push forward of the square of psi n plus 1 to the, well, push forward of the psi n plus 1 squared, where pi is the forgetful map. It forgets the mark point with number n plus 1, and the push forward is just the integration along the fibers. So psi n plus 1 is a two-dimensional cohomology class. The square is four-dimensional. We integrate along fibers that are surfaces. They are two-dimensional. We get again a two-dimensional cohomology class that is denoted by K1, the first Malford class. And this actually provides a possibility to approach the Peterson volume by the intersection theory and the modular space MGN bar. So now I'll tell how the Weil-Peterson volumes are related to intersection numbers of side classes or endpoint correlators. So to do this, let's consider the genus expansion of the total free energy. Fg is the genus G contribution to the total free energy F. And let us consider the generating function of Weil-Peterson volumes that we denote by VGN. Here, genus G is fixed, and the number of mark points changes from 0 to infinity. So we consider such a generating function, and then this function can be expressed in terms of the total free energy as a specialization of this series, namely to get the generating function for the Weil-Peterson volumes, we put the space variable T0 to be x, the first time to be 0, and other times should have the form 1 minus 1 to the I over I minus 1 factorial. That's for I larger than 1. So that means that Weil-Peterson volumes can be expressed as certain sums in endpoint correlators.
Hello.
So now,
there's another question. Can we ask a question?
Yes, but please, can you speak louder?
Yes, Anton will ask a question.
Okay, so this Wolfert formula that the push forward of psi square is kappa, is it a difficult fact, or like is it an elementary calculation, or how complicated is it?
Well, it's actually a topological result. Yeah. It goes like follows here. Wolfert constructed a representative family of 2 cycles, and then he integrates both Weil-Peterson form and kappa class over these 2 cycles and gets the same answer. So that's how he proved that the Weil-Peterson class is the same as kappa 1.
Okay, thank you.
Thank you. Please go on.
Okay, so now let's discuss the asymptotics of Weil-Peterson volumes. First, let's consider the case that is somewhat simpler. And in this regime, n tends to infinity and G, the genus, remains fixed. Then one has the following asymptotic expansion. Vgn is the Peterson volume of the modular space Ngn. And the structure of this formula is like this. There is a factorial term, n factorial. Then there is an exponential term, c to the n. Then there is power term, n to the power 5 over 2g minus 7 over 2. Yeah, and then there is an asymptotic expansion in the inverse powers of g. This formula was derived by Mann and myself. And here, c is given by an explicit formula, namely it's minus 2 over x naught g naught prime of x naught, where x naught is the first positive zero of the Bessel function j naught. Moreover, say these coefficients bgi are effectively computable. There is a procedure that allows to compute them. That's not a simple algorithm, but it's in principle doable, at least for small g. And for instance, if we consider the constant term, bg naught, then these constant terms are the coefficients of the so-called instanton solution to the first Spengler-Weyl equation. So you see two interesting functions appear in the asymptotics of Petersson volumes, namely the Bessel function j naught and the instanton solution to the Spengler-Weyl equation. Well, in a low genus, one can get formulas that are more explicit and more illuminating. Let's denote by y of x the second derivative of phi naught of x. Let me recall that phi naught of x is the generating function of genus 0 L Peterson volume. Then let's take the function x of y that is inverse to y of x. And this function, x of y, is quite explicit. It's given by this formula, minus square root of y times g naught prime of 2 square roots of y. So that's where this Bessel function appears from, and is given by a simple power series like this. That's an observation by Kaufman, Manning, and Zagier. For small g, one can also get explicit formulas for the generating function of genus G, Weyl Peterson volumes. For example, if we take g equal to 1, then phi 1 of x is 1 over 24 times the logarithm of y prime of x, or the third derivative of phi naught of x, which is this. For g equal to 2 or larger, then the generating function is a homogeneous differential polynomial in y prime of x, and its coefficients can also be computed explicitly, but again, not fast. So good with a large N asymptotics, and let's now discuss the large G asymptotic. The asymptotics of the Petersburg volumes as G tends to infinity and number of arc points remained fixed. So I designed an official algorithm for computing Petersburg volumes some time ago, and it allowed me to compute Petersburg volumes up to G equal to 75 with for small values of n. And analyzing this numerical data, I came up to the following asymptotic expansion. So the Weil-Petersen volume of MGN, where n is fixed and G tends to infinity, has the following form. The first term, the leading term, is 2G factorial. Then there is a power term, exponential term, 2 over pi squared to the G. Then there is a power term, G to the n minus 7 over 2. Then there is the constant term, 2 to the 2n minus 6 over square root of pi. And there is an asymptotic expansion in the inverse powers of G. So a few words about justification of this formula. Before my conjecture, it was known that the first term is 2G factorial. Actually, an estimate of it was obtained by Bob Penner, and later Sam Gruszewski refined his argument and proved that for n equals 0, it's precisely 2G factorial. Then Schumacher and Trapani extended Gruszewski proof to the case of arbitrary n. So this term was known. What concerns other terms, they were not known, and the exponential term was first proven by Mirza Highness. And then we combined our efforts and proved the power term and the asymptotic expansion, and the existence of the asymptotic expansion in inverse powers of G. What is not done, there is no justification of the constant term. It's still elusive. That's because we study the ratios of volumes where this term gets cancelled, but the accuracy of computations leave no doubt that this number is like here, so it's essentially square root of pi. But again, there is no proof of this yet. The coefficients of the asymptotic expansion, they also have an interesting structure. They are polynomials in n of degree 2i with coefficients in the polynomial ring generated by pi squared and pi squared inverse. And numerical data suggests that the coefficients of the polynomial Cni actually belong to the polynomials in the inverse square of pi. The simplest example is the formula for Cn1, and it's given here at the bottom of this page. So now let me finish with the Highness Peterson volumes. These volumes appeared recently in a paper by Saad, Schenker, and Stanford on JT gravity. So Mirza Highness considered the following modular space. She took the space of G hyperbolic surfaces with n geodesic boundary components of lengths L1 to Ln. This is a no default, but it doesn't have a complex structure. At least it's not known. However, it has a symplectic structure, a symplectic form that extends the Weil-Peterson form. When all lengths are 0, then we get just the ordinary Weil-Peterson form from MGN. That is done using the formula for the Weil-Peterson metric, also Weil-Peterson symplectic form in terms of length twist parameters, and it generalizes to the case of bordered Riemann surfaces. Mirza Highness showed that Weil-Peterson volume of this modular space is finite and given as a series, actually as a polynomial in Li's, whose coefficients are certain intersection numbers that I'm going to define now. So they differ from endpoint correlators by adding the power of the kappa-1 class in such a way that the sum of these is the dimension of the modular space. In this case, we can integrate this product and get an intersection number that is relevant to GT gravity. So this intersection number is the integral over the Riemann compactification of kappa 1 to d naught, psi 1 to d1, and so on up to psi n to d. And for large G, we got the following asymptotic expansion. So when G becomes large, normalized intersection numbers tend to the limit that is explicitly given by this form. It was first conjectured by me on the basis of numerical evidence and proven by Mirza Highness and myself. So I think I'll stop here. Thank you for your attention.
Very much. So I already see one question, please.
Sorry, in this last formula, this VGN, that's just the ordinary Weil-Peterson volume, right? Or,
yes, that's true.
and this is a natural normalization because it also, right? It would also kind of grow with G.
Please speak louder.
So why is it it's a natural normalization? Because they would have a similar growth with G. Well,
Sorry, can you please repeat?
Could you speak upwards towards the mic? Maybe it will be clearer.
One sec, we're solving the technical issue. Speak where?
Upwards, that's the mic.
Upwards. Well, yeah. So why this 1 over VGN? Is it a natural normalization? So they have a similar growth with G, or kind of why you divide by?
Okay,
VGN?
so VGN is the constant term in Highness formula, Highness polynomial for the VGN of L1 to Ln, just on top of this page.
Oh, that's where all DIs are 0 with respect with the
Yes.
exception of D0, right?
Yes, yes. And it's natural to divide by the constant term, and then there are limits.
But do you know all those like G to infinity asymptotics, kind of how physicists call them in some way? What are the physics words attached to it?
Well, that I don't know.
Well, I mean, actually, we have time for questions, but I have one in the meantime if people want to think, which is possibly related to what Anton was asking. So,
I can just comment the following, that Stanford contacted me. He was interested in the numbers K1 to D0, tau D1, tau D2. So he was interested in volumes of bordered surfaces with precisely 2 boundary components. And the numerical data that I sent to him somehow suited well for his theoretical computations. That's essentially all that I know.
so,
but I would like to get a better knowledge of this, but not yet.
one question might be that if you know the large order behavior, can you actually say something about what we would call non-perturbative contributions, so that are not like powers of G, but exponentials of G? So could you do some resummation of your results at large orders and, you know, find out about these kind of e to the -1 over G corrections?
No, that I don't know. Never thought about that.
Okay. There's one more question, but maybe come here and there's one more question. 1 second, we need to go to the microphone.
I would like to ask, is there any like a cut and paste method to calculate these numbers? The cut and paste of this J and N?
Sorry, please, can you repeat?
The question was whether there is a so-called cut and paste method to calculate the volumes. Do you want the volumes?
This number.
No, I don't know.
Thank you.
Are there any more questions or comments? Okay, well, I think in that case, we would like to thank you again for your very nice talk.
Thank you.